Module 3 of Chapter 20 is going to introduce two variations on Brownian motion that introduce some characteristics that are useful in certain models and also have problems potentially as a stock model. And in the next module, Module 4, we'll look at the variation on Brownian motion which will in fact be our stock model. First of all, there's what's called arithmetic Brownian motion. And all arithmetic Brownian motion does is to introduce a non-zero mean drift and a variance that's not equal to 1. And it does that in a way that, first of all, the change in the variance, the multiplier of dz by sigma, if dz is normally distributed with a mean, if it's apparent that if dz is normally distributed with a mean of 0 and a variance of dt, then if I take sigma dz, it's equally apparent that that's normally distributed with a mean of 0 and a variance of sigma squared dt. So shifting the variance from 1 to sigma squared is easily accomplished simply by multiplying dz by the coefficient sigma. That's easy. We then have a drift term. Now notice that this alpha dt is saying that over any interval of time, the change in x is going to start off being alpha times the change in time. So we're introducing a drift, and what that does is shift the mean of the distribution. So that ultimately, from this analysis, we'll see that dx with arithmetic Brownian motion has a normal distribution, and the mean is alpha dt, and the variance is sigma squared dt. So with this shift in the drift and the multiplier of sigma, we're able to move both the mean and the variance of the changes in this process. It's called arithmetic Brownian motion. Alpha we can think of as the mean, instantaneous mean per unit of time. That's why we're multiplying it by dt. So you can think of alpha as being an annual value if time is in years, and then I multiply alpha by dt or delta t, and that gives me the increment for that period of time. Sigma squared is the instantaneous variance, again, much like all the sigma squares we've been dealing with before, and it provides the variability of the process. So we have, by virtue of the formula we saw a moment ago, which is to say, if every change in x is normally distributed, I forgot an end there, if every change in x is normally distributed, then apparently if I add up a number of these changes, they're also normally distributed. And the slide that we were just getting to articulates that here. It says that the change in x from 0 to time t, well, that's a sum of a large number of dx's. Each dx is normally distributed. So the sum is normal. That's what that says. And then secondly, what's the mean? Well, the mean of a sum of normal variables is the sum of the means. So instead of having alpha dt, if we add up a number of alpha dt's, we get alpha times the total time interval. Similarly, what's the variance of a sum of normals? Well, we're assuming independence because the dz's are independent. If we have independent normals, the variance of a sum is the sum of the variances. And once again, we get the sigma squared dt. So arithmetic Brownian motion provides you with a process where the value of x at time t is going to be equal to its initial value plus a normally distributed random variable whose mean and variance grow linearly in time. Not a very appropriate stock price process,